Hi, in this video, we're going to talk about the flow network and the max flow problem in a flow network. So previously, we've used a directed graph to represent a map, and then we studied the Dijkstra algorithm that can get us from one vertex in the map to another in the shortest distance. So now, as we mentioned previously, a graph can represent many other things, right? So one of those things include what's called a flow network. So in a flow network, it looks, well, it's just a graph, right? But the number of each of the edge, instead of representing the distance between two vertices, it actually represents what's called a capacity. And that the capacity is how much materials can flow through that edge. And then of all the vertices, there are two very special ones, and one is the source. In this case, it's the vertex A, or often it's denoted with the S. Right? This is the source is a vertex that produce materials and send them out. And then there's the other special vertex. It's what's called a sink, which receives the materials and very likely consume them, right? So now what's shown here in the graph, hopefully you can see that there's the path between the source and the sink is there are multiple paths. So it can go through this path here, it can go through this path here, and it can actually even go through this path here. So between the source and the material, there are multiple paths. And also, in a more complex flow network, there are multiple sources and sinks. Although for our study of the max flow problem, we always assume just a single pair of source and sink. So what's a real world example of a flow network? So one would be kind of a water distribution network. So in this network, the source, I think it's shown here, would be a water tower, right, which store a lot of water and then it supplies the water to the rest of the town or city. And so the sinks then are the residential units, your house, your apartment that you live in. So, and that's the place where we use the water, consumes the water. So the edges in the system would be the pipes, the water pipes that the water would flow through. So and there, if you've ever seen pipes before, some of them are very with a big diameter, it's very thick. Others are kind of smaller, so with smaller diameter. And kind of the diameter of the pipes would more or less determines the flow of the water or the capacity of the pipe, right? So higher the capacity, the larger the diameter, the more water can flow through it. And in terms of the capacity, it's usually specified in volume per second. So let's say cubic meter per second. So that's one example. Other examples could be in an auto assembly line. I mean, there are parts that can be carried and used kind of throughout the assembly line. Or if you think in terms of, let's say, UPS or FedEx, they have many in their delivery network. There are many hubs where the goods that they deliver would kind of travel between these hubs, and between hubs there are they might um, they might have more trucks going between hubs that carry a lot more goods, and or they might have fewer trucks going between hubs that don't carry that many goods. So that's another example of a flow network. And then finally, another example here is, imagine there are lots of actually information that flows between, say, the Google servers and your smartphones. And the whole network is very connected. There are multiple ways for data to travel, between the servers and the clients, your phones. So the internet is, in some ways, especially if you look at the capacity or the bandwidth of the pipes in the internet, that's very much like a flow network. So with a flow network, one of the most common problem we want to solve is what's called a max flow problem. So the max flow problem is basically given a source and a sink, what is the maximum materials that can be sent from the source and the sink. So one thing I just want to point out is because as we said before, there can be multiple paths that connect the source and the sink. So the max flow is the sum of all the flows through all these paths. So this is an example of the max flow problem in this small network of 4 nodes and 5 vertices. Again, these numbers along vertex means the capacity of the edge. So for example, in a water distribution system, this could mean this edge or this pipe allows 3, say, cubic meters of water to flow through it per second. So think about what is the maximum flow that can go from the source to the sink in this case. Well, as it turns out, and if you look at this long enough, the maximum possible flow is 5. So this is the actual max flow graph. So these numbers are now the flow, not the capacity anymore. So these are the flow. So what this graph is saying is that I can send 3 cubic meters of water from A to B, and then those 3 cubic meters of water get split into 1 cubic meters of water along this edge and 2 cubic meters of water to this edge. And then the same thing for this edge, except it's sending out 2 cubic meters of water per second. So 1 cubic meter of water, 2 cubic meters of water, the sum is 3 cubic meters of water, which can go through this edge to the sink. So if you add the final kind of what's being produced at the source, total of 5 cubic meters of water per second, and what goes into the sink, which is 5 cubic meters of water per second. So that's an example. Now, if you actually look at the max flow algorithms, there are several of them out there. We'll study what's called the Ford-Fulkerson algorithm, and your assignment will be to implement this. So, okay, we already talked about this slide, and so now before we talk about the algorithm, there are several things about the flow network that we really should know. So these are called properties or invariants. They're things that should be obeyed all the time for the flow network. They got interesting names, but most of them are fairly intuitive. The first of such properties is called the capacity constraint. So all that is saying is that the flow must be less than or equal to the capacity, which again should make totally intuitive sense because it basically says we cannot send more material through the pipe than its capacity allows. And since we often talk about flow and capacity, and we often want to see them together, so a lot of times we denote the flow and the capacity in the form of flow slash capacity. So in this very simple network, the edge has a capacity of 5, and right now we're sending a flow of 3 through it. So it's 3 over 5. So the second of such property is what's called a skew symmetry. And all it says is that the flow in one direction is the same as the negative flow in the opposite or the reverse direction. So an example here is there's a flow of 4 from A to B, right? And that is exactly the same as a flow of negative 4 from B to A, right? Negative, you get back positive. So that's all it is, skew symmetry. Okay, so the last property is what's called the flow conservation, and we kind of already talked about it when we went over the example. So a little more formally, it says that the total flows going into a vertex is exactly the same as those going out. So we are not gaining any additional materials just going through a vertex. We're not losing any materials. And obviously this does not apply to the source and the sink, because the source produce materials and the sink would consume materials. Okay, so now given that definition, here are some flows. So take a look at through them and see which of them actually obeys the flow conservation and which of them do not. And assuming you've done that, here's basically the answers. And these two, they do obey the flow conservations, and this one definitely does not, right? 2 units of materials goes in, 5 comes out. That's not good. And here, this one doesn't obey that either. The total going in is 9. The one going out is just 3.